Welcome back to the deep dive. We often run into problems that, look deceivingly simple on the surface, but when you dig in, you find this deep, hidden complexity. And today, we're peeling back the layers on one of those exact problems, rectangulations. Our listeners sent over some fascinating source material on a recent breakthrough in computational geometry, specifically an algorithm from Marino and Muetza in 2021. So our mission today is pretty straightforward. We want to deep dive into the C++ blueprint that lets a computer systematically, efficiently generate every single possible way to partition a rectangle into smaller pieces. We're talking about an engine that can just crank out millions of unique geometric designs a second.
It's a really classic area of study, actually. It's called combinatorial enumeration. And when we say rectangulation, what we mean is taking a big rectangle and partitioning it into smaller ones, using only straight horizontal or vertical cuts. The researchers call them walls. And the one strict rule is that these walls can't cross each other in the middle. They can only meet at their endpoints.
Okay, let's unpack that. Because if you just grab a pen and paper, it feels simple enough.
It does.
But the sources immediately show you how adding constraints just creates this entire universe of possibilities. They define three distinct classes.
Exactly. And what defines them is just how restrictive you are with placing those walls. So we start with the broadest class, the most unconstrained one, generic rectangulations.
And here, the walls can basically stop and start wherever they want, right? As long as they don't cross.
That's the one. And this is where the numbers just explode.
Right. The sources show that if you want, say, 5 interior rectangles, the number is manageable, less than 200 ways. But if you push that to n equals 10, suddenly you're at approximately 10 million configurations.
A super exponential growth rate. I mean, that sheer volume is exactly why you need a ridiculously fast algorithm to even begin to explore it.
So then you swing to the complete opposite end of the spectrum, the really structured one.
Yes, the diagonal rectangulations. And this class has a very, very strict geometric rule.
Okay, what's that?
Every single internal wall has to touch the main diagonal line of the big bounding rectangle.
That seems like a really specific constraint. Does that simplify the math a lot?
Oh, it makes it beautifully predictable. When you add that one rule, the number of configurations stops exploding. Instead, it follows a classic mathematical sequence.
The Catalan numbers.
The Catalan numbers, exactly. So for n equals 10, instead of 10 million, you only have 4,862 possibilities.
Wow. That's a huge drop in complexity from just one rule.
A massive drop. It's a great example of how geometry really drives the math here.
And sitting between those two extremes, there's an intermediate class.
Right, block-aligned rectangulations. It's a subset of diagonal where walls have to line up with block boundaries.
And the growth rate there is somewhere in the middle.
Somewhere between the super exponential chaos of generic and the, predictable exponential growth of diagonal.
What's so important to remember here, and the sources stress this, is that these aren't just abstract drawings.
Not at all. That's what makes this so important. The practical applications are huge. Think about VLSI design.
Very large-scale integration. So designing computer chips.
Exactly. Placing components on a chip, routing connections efficiently, that is fundamentally a rectangulation problem. And the same ideas apply in architecture or urban planning. You're trying to maximize floor space or define city zones. These geometric models translate directly into real-world efficiency.
So you have this massive landscape of possibilities, especially in that generic case. 10 million paths just for 10 rectangles. The challenge isn't just counting them.
No.
It's designing a reliable GPS system to visit every single one, systematically. No misses, no repeats.
And that's the genius at the heart of the algorithm. They imagine this entire universe of possibilities as a adjustment network, a state graph, where every valid rectangulation is a city on a map. The goal then becomes finding the perfect tour of all those cities.
Wait, hold on. A perfect tour. If every configuration is a city, you're talking about a tour that visits every single city exactly once and then comes home.
That is the literal definition of a Hamilton cycle.
Ah.
It's the optimal path. It guarantees you cover every vertex, every design exactly one time. And once you have that cycle, generating them is just a high-speed walk along that path.
And moving along this path, it's not like you're completely redrawing the rectangle each time, is it? The sources say they use tiny local shifts, these jumps.
Exactly. The shift is minimal. It's just a local tweak of a single wall or a junction. So the computational work between states is incredibly small.
And that's what lets the C++ code move from one state to the next almost instantly.
That's how you get to millions per second.
Okay, that makes perfect sense for the generic case where anything goes. But here's the puzzle for me.
Mm.
How do you stay on track? How do they make sure a jump stays within the rules of, say, the diagonal class?
That's a great question. And it's one of the biggest insights of the study. They handle it through something called pattern avoidance.
Better to avoid.
Yeah, so instead of writing a whole new algorithm for the diagonal case, they just start with the huge generic universe and define a few geometric structures that are, well, forbidden.
So you manage the complexity not by defining what you can do, but by defining a few things you absolutely cannot do.
Precisely. They defined 8 specific forbidden patterns, little local structures like a clockwise windmill or different brick patterns. You just tell the algorithm, if a jump would create this pattern, that path is blocked. Don't go there.
That feels like a really powerful idea. Can you give a concrete example of how that works?
They show it perfectly with the diagonal rectangulations. You can get that entire well-behaved set of 4,862 configurations.
For n equals 10.
For n equals 10, yes. You get all of them simply by forbidding 2 little local patterns, the left-right brick and the bottom-top brick.
That's it. Just forbidding those two things.
That's it. You forbid those 2 structures, and you instantly wrestle a 10 million solution problem down into one that follows the simple, classic Catalan numbers.
That is a true aha moment. It means they've found the absolute minimum rules needed to impose order on all that chaos. So let's get into the choreography of these jumps. What are the actual moves?
The transitions rely on a toolkit of 3 main types of local transformations, 3 jumps.
Let's start with the workhorse, the W jump.
The W jump or wall jump is the most common one. It's where a wall effectively shifts its attachment point. Imagine a vertical wall that ends on a horizontal one.
Okay.
The W jump slides that vertical wall just past the junction, so it sort of jumps over the endpoint and reattaches somewhere else. A very slight, very local change.
So if it's so common, why isn't the W jump enough to visit everything? Shouldn't that one simple shift cover all the bases?
You'd think so, but no. Sometimes the geometry gets so tangled that a simple W jump would either break the rules or it would take the algorithm off that perfect Hamilton path. And that's where the S jump or special jump comes in. It's a much more complex transformation for navigating those really awkward transitions where a wall jump just won't work.
The exception that proves the rule.
Pretty much. And then there's the third one, the T jump.
For T-junctions, I assume.
Exactly. Where 3 walls meet, the T-junction jump reconfigures the junction itself. It's another necessary move to make sure every single state is reachable.
This all sounds like it requires incredibly sophisticated management. How does the algorithm know that when it does a WS or T jump, it's staying on the right path, especially if pattern avoidance is turned on?
This brings us to maybe the most critical control feature, the lock and unlock mechanism.
Oh, kind of lock.
This system is designed precisely to manage which parts of the rectangulation can and cannot be changed during a move.
So the algorithm is essentially putting a temporary do not move sign on certain walls.
That's a perfect way to think about it. A lock operation marks a wall and its edges as fixed temporarily. This is crucial for guiding the path.
So it ensures a jump over here doesn't accidentally create a forbidden pattern over there.
Exactly. Or break the diagonal constraint, for example. And then once the jump is done and that constraint isn't needed anymore, an unlock operation removes the sign, making that wall flexible again for future moves.
That is some really sophisticated control. So it's not just reacting to the geometry.
No, it's proactively managing it to guarantee the path is perfect.
And all of this logic checking, the type, the patterns, figuring out which jump to use is all wrapped up in one core function.
Yep, they just call it next. It's the brain of the whole operation.
Okay, let's pivot from the theory to the engineering. This wasn't just a math proof. It became a high-performance C++ tool. What makes the implementation so fast?
Well, it starts with the data structure. The way it's all stored in memory is incredibly efficient. It scales linearly, which means the memory footprint stays small even for really big problems.
And the code is built to be adaptable.
Very. They use some robust software design principles. For example, the strategy pattern is used to handle the different rules for generic, diagonal, and so on.
So if you want to switch from exploring generic to diagonal, the code just slops its strategy.
It does it seamlessly. And similarly, that lock and lock mechanism we talked about is built using the state pattern, which keeps the management of wall states really clean and reliable.
So let's talk numbers. What does the performance actually look like when you benchmark it?
The data is pretty stunning. We mentioned the 10 million generic configurations for n equals 10.
Right.
This algorithm can generate and list every single one of them in about 300 seconds.
5 minutes.
5 minutes.
5 minutes to explore the entire theoretical universe of designs for a 10-block floor plan.
And that speed is pushed even further with optimization. They point out that standard C++ compiler flags like Natishow 3 give you a 3 to 5 times speed up right away.
Wow.
And then on top of that, they add their own algorithmic tweaks for even more gains. It's a very highly tuned piece of software.
So, bringing this back to our listener,
Mhm.
what does an engine like this unlock for those real-world applications? Why should a VLSI designer or a data scientist actually care about this?
Because it turns design from an exercise in pure creativity into an exercise in selection. For data visualization, this is the engine behind tree maps.
Right, where the size of the rectangle shows the value of some data.
Exactly. This tool lets them explore every possible layout to find the most readable one. For computational geometry, it's the engine for mesh generation or spatial indexing.
And for computer graphics, too, I'd imagine.
Absolutely. Texture mapping, scene partitioning. Anytime you need to divide up a complex space in the most efficient, structured way possible, this algorithm gives you the complete answer key. It just hands you the entire design space on a platter.
This has really been a fascinating deep dive. Let's summarize the key takeaways for you. First, we explored this vast landscape of rectangulations, from the chaotic generic class to the beautifully ordered diagonal class, all just defined by simple rules.
Second, the really elegant solution to generating them all, building a Hamilton cycle in the state graph. That guarantees every configuration is visited exactly once through these high-speed local jumps.
Third, the nuts and bolts of it. The combination of the three jumps W, S, and T all, carefully choreographed by that very clever lock-and-lock mechanism to keep the algorithm on its perfect path.
And finally, the huge practical relevance. This lightning-fast tool provides the foundation for modern design, whether you're trying to optimize a microchip or visualize a massive data set.
We've seen that this algorithm can exhaustively map every theoretically possible design, 10 million of them, in just 5 minutes.
And this raises a really powerful question for the future of design. If a machine can explore every valid configuration, every possibility in the time it takes a human to draw just one sketch,
Hmm.
what does that do to the role of human intuition? Are architects and designers becoming less about generating possibilities and more about applying their unique insight to select the single best design from a machine-generated infinity? Something to chew on as you plan your next perfect space.